Hello and welcome to the second to last lecture in Introduction to Astronomy. This is lecture 19, Hubble's Law, where we will discuss how we can tell that the universe is expanding and how we can do that by studying galaxies. So in this lecture, we will learn about extragalactic studies and how the first other galaxies than the Milky Way were discovered and confirmed. And that was with Andromeda, known as Messier 31, M31. And we'll learn how Edwin Hubble determined that that was indeed another galaxy. We will then talk about the three different types of galaxies that are found in the universe. And then we will move on to Hubble's law and what that means for the history of the universe. Then we will talk about quasars and supermassive black holes and how they are related to galaxies. And lastly, we will use Hubble's law to determine how old the universe is by rewinding the clock based on what we can tell from the expansion rate. So it wasn't actually known that the Milky Way was just one of many galaxies. It was thought that the Milky Way was the entire extent of our universe up until about 1924. So it's really only been about 100 years that we've known that the Milky Way is just one of billions of galaxies. So the early detections were really not quite resolved. They couldn't make out features in the distant galaxies to actually determine that they were distant galaxies and not just nebula contained within the Milky Way. So for a while, the Andromeda galaxy was known as the Andromeda Nebula. But today, with our technology, even your cell phone can take a picture of Andromeda. So below is a picture of Andromeda taken with a Google Pixel 5 cell phone. So it's really incredible that now something that you have in your pocket is capable of not only resolving that many stars, which I think is impressive for a phone, but being able to pick out another galaxy. So in 1925, Edwin Hubble discovered that the Andromeda uh, galaxy, uh, at the time it was the Andromeda Nebula, he calculated that it had to be 900,000 light years away. That was the furthest distance of anything measured at the time, and that ignited the brand new field of extragalactic astronomy. We now know that Andromeda is actually 2.5 million light years away, but Edwin Hubble's discovery was good enough to prove that it was indeed another galaxy and not something within our own galaxy. And for reference, the Milky Way is about 100,000 light years across. So if something was 900,000 light years away, it was definitely outside the Milky Way. So after Edwin Hubble discovered that these smudges in the sky, some of them were other galaxies, other people began to peer more closely at the known nebula to see if they were other galaxies, and they took notes to describe the properties of these other galaxies. And so, as it turns out, most of the galaxies that are very large and luminous they come in two main shapes: spirals or ellipticals. But you can also find some smaller galaxies as irregular. So spiral galaxies are, as you would expect, spiral shaped. They have a central bulge with some halo stars around it, but they are primarily defined by their disk along with their spiral arms. And spiral galaxies can be either barred or unbarred in their center. Generally, they contain young hot stars and have active areas of star formation, but they have a good mix of old and young stars as well. Elliptical galaxies are filled with mostly old stars that are in globular clusters. In fact, the whole galaxy is kind of in one large ellipsoidal cluster. It does not have very much interstellar material, so it doesn't have a lot of spare gas and dust to make new stars. And so it is primarily composed of just older stars. They can be quite small, these elliptical galaxies, or they can be incredibly large. In fact, the largest known galaxies are elliptical galaxies. And lastly, we have the irregular galaxies. This is a pretty broad classification that's just given to galaxies that don't have a spiral or an elliptical shape. They are often low mass and appear very disorganized with lots of intense star formation. And this hints that maybe they had a recent gravitational encounter with another galaxy that disrupted their shape, stirred up the gas and dust, and spurred on that new star formation. Often irregular galaxies can be found near other galaxies. But unlike stellar evolution, there's no well-defined mechanism for how galaxies evolve over time. There's not one rule which describes how galaxies evolve. It's quite a messy area, but it's fascinating to study, and I think it's one of the coolest areas because there's still so many open questions and so many examples to study. So it's an emerging field in astronomy, and I think it is one of the coolest. So one of the most important properties of galaxies is their mass, how much stuff there is in that galaxy. So for spiral galaxies, the mass is pretty easy to measure. Since we have a lot of things moving around, rotating, and we can check their rotational speeds, we can calculate how much mass there is in that galaxy. Unfortunately, elliptical galaxies and irregulars don't have that systematic rotation, but the astronomers can use other methods to determine how much gravitational uh, force or how much mass there is that is causing the gravitational interactions that they can observe in these elliptical and irregular galaxies. And so, using those methods, they find that the most and least massive galaxies are actually elliptical. While on average, irregular galaxies have less mass than the spirals. Spirals kind of run the middle of the mass ratio, and then we have the irregulars being usually less massive than the spirals, and then ellipticals being the most massive and least massive. Another very useful property of galaxies is their mass to light ratio. How much mass do they have in comparison to how much light are they giving off? And this tells astronomers roughly what type of stars make up the most luminous population of that galaxy. They can determine statistically who are the most common types of stars in that galaxy based on their mass to light ratio. For stars in most stars in galaxies are low mass, and this gives a mass to light ratio greater than 1 depending on the ratio of high mass stars to low mass stars. Generally, galaxies with active star formation will have a higher ratio because they're making a lot more massive stars, which are going to be short-lived, while older galaxies are going to have a ratio that is about 10 to 20. The mass to light ratio, though, is independent of dark matter, which can contribute a lot of mass without contributing any light. So if you remember our cosmic distance ladder, we started with radar ranging to find the distance to Venus and the Sun, and then we used parallax to determine the distance of nearby stars, and then we used main sequence fitting to determine the distance of clusters in our Milky Way. But how can we determine the distance to other galaxies? So we need to know the distance to other galaxies if we really want to know the other features of them very well. But apparent brightness and distance are both correlated to luminosity. So we need to know the luminosity of something in another galaxy. So this is one of the most difficult problems to overcome in extragalactic astronomy. So variable stars in distant galaxies can help determine their distance. However, Cepheids have only been detected in a small number of galaxies, and even today, the distinction between individual stars is very difficult to determine within other galaxies because they're just so far away. We don't quite have that resolving power for the galaxies that are way more distant. However, we are not out of ways to measure distance. Type 1a supernova have a standard luminosity. They act as a light bulb because they have nearly equivalent luminosities. And so if one observes a type 1a supernova, we know that luminosity, and so we can then determine the distance. But type 1a supernova aren't going to occur whenever we want them to determine the distance, so we have to use other methods as well. So there is what astronomers call the Tully-Fisher relation, which relates the rotational velocity of a spiral galaxy to its luminosity. And so it works pretty well, but it has a wider range of uncertainty because it depends on more less well understood facts. So by studying the light of distant galaxies, we can actually determine some really interesting things about our universe. So while studying spiral nebula, because this is back when before we knew that there were other galaxies, Percival Lowell and Vesto Silfer stumbled upon a very important discovery. They found that the spectral lines in these spiral nebula exhibited significant redshift, and that these then unknown to them as galaxies, but now we know them as galaxies, were racing away from them at speeds as high as 1,800 kilometers per second. So back in 1914, when they made this discovery, no one quite understood the implication of this. What did it mean for everything to be racing away at higher and higher speeds? Until Georges Lemaitre published an obscure French article called "A Homogeneous Universe of Constant Mass and Growing Radius Accounting for the Radial Velocity of Extragalactic Nebula." This actually showed that using Einstein's equations of relativity, they were consistent with a universe that was expanding. Shortly after, Edwin Hubble, along with his collaborator Milton Humason, they confirmed this. Milton Humason is a fascinating character. He was an 8th grade dropout who was a mule train driver, so he was just keeping the mules on course. And then he worked as a janitor, and then he became a night assistant at an observatory, and then he became a fully fledged astronomer. So using their measurements of extragalactic distances along with Silther's data, they found that these distant galaxies were moving faster than closer galaxies. The further away a galaxy was, the faster it was moving away from us, the observer. And so in 1931, Hubble and Humason published their paper which directly compared the distance to the velocity of recession. And they showed and proved that the universe was expanding and that expansion was accelerating. This relationship of the distance something had with how fast it was moving away from us became known as Hubble's law. And so you could calculate the distance of something from its velocity using Hubble's constant. But Hubble's law is not quite so perfect and smooth in the real world, and Hubble's constant is actually time dependent, and it only becomes about 22 kilometers per second per million light years for distant galaxies that we can observe. So that means that for every million light years you look further away, the galaxy that you see is going to be moving 22 kilometers per second. So a galaxy that's 1 million light years away will be moving about 22 kilometers per second. A galaxy that's 2 million light years away will be moving about 44 kilometers per second. And we will have to assume that Hubble's constant is a universal constant for all galaxies. So this has some major implications. We can find distances and complete the cosmic distance ladder. Hubble's constant implies that the universe is expanding, and that expansion is accelerating, given that the further away something is, the faster it is. The changing speed is an acceleration. And by taking the inverse of Hubble's constant, which has units of speed per million light years, we can actually find the age of the universe, because the inverse of that would be an inverse, would give us a time. And so if we convert those seconds to years, we find that the universe is about 13.6 billion years old. But if the universe is expanding, how can that expansion be speeding up? Wouldn't gravity be slowing it down as it expanded? Wouldn't all of the matter be pulling on all of the other matter and stop it from moving away? But this is not what we see with the data. And so astronomers are quite confused because there's no known force in nature which can account for this acceleration, which we see in our observations. We're going to need something to help explain that. So now astronomers were really curious about what was happening to the universe. How were things expanding? And we needed to look at the furthest objects possible to really pinpoint what was happening. So astronomers looked at the brightest and furthest things that they could find, and that helped discover the quasar. That was one of the things that they discovered. Quasar stands for quasi-stellar object because it was kind of star-like. These were very bright points, but they didn't quite have the properties of stars. They had very different spectral lines. It was like they were almost entire galaxies, but they were so far away that they appeared point-like. And so they were discovered in 1950 with the radio equipment left over from World War II, but it wasn't until 1963, when looking over the spectra, that these were determined to not actually be stars, but entire galaxies. So in 1963, Martin Schmidt showed that the spectra from these quasars resembled the hydrogen Balmer lines, but that they were redshifted to extreme ends. But one could not imagine a star within our own galaxy that could have that much redshift. It would have to be something extremely far away. And it had to be something that was outside the Milky Way. And so this, combined with later observations, showed that these quasars were distant galaxies because they emitted bright infrared and X-ray radiation. And now there are over a million known quasars, all which show extreme redshifts and no blue shifts. They're not moving towards us. They are moving extremely quickly they're moving extremely rapidly away from us. But they still have some parts in the visible spectrum, just like stars. So quasars are very bright and luminous, distant galaxies. But why are they so bright and luminous? So to truly understand these quasars, we need to know their distance. How can we prove that they are outside the Milky Way? Hubble's law is the most effective method for determining these distances. But do we know that they actually apply? After decades of observations, astronomers have shown, using the Hubble Space Telescope, that quasars do obey Hubble's law, that their recessional velocities are lining up with their distances, and that they are indeed outside our galaxy. Quasars are located at the center of galactic nuclei, and they are the earliest galaxies which form in the universe. So they are so bright that they the central part of the quasar outshines their host galaxy by a factor of 10 to 100 times. So this means that quasars are truly outputting an insane amount of energy, unlike anything we've ever seen. They are so bright, in fact, that they are detectable as points of light, which are brighter than the galaxy that they're contained within. So what is causing these galaxies to have extremely bright points? And how can this tell us about the universe? So quasars are outputting an incredible amount of energy. They are located in galaxies that are incredibly far away, and they outshine their entire host galaxy. Looking at the spectra of quasars, we find that they have emissions from radio waves all the way up to gamma rays. And this is not corresponding to any known fusion process. So it wasn't until the 60s, with the discovery of Cygnus X1, a black hole, that the mystery of quasars really began to be illuminated. So, after several decades of accumulating evidence and observations, astronomers hypothesized that quasars are actually supermassive black holes that are rapidly accreting material and really giving off tons and tons of energy. And we find today that many galaxies, many just regular normal galaxies, have supermassive black holes at their center. And so, with our measurements, there is a lot of evidence that these quasars are indeed supermassive black holes at the center of distant galaxies that have masses up to 1 billion times that of our sun. And so, this means that the Milky Way's central supermassive black hole is too light to be a quasar. A quasar is a black hole that in the center of a galaxy that has at least 1 billion times the mass of the sun, and it is giving off lots of intense radiation. So by studying the light from these distant quasars, astronomers can peer into the conditions of the early universe. This makes them an excellent probe to look at what the universe was like after it was born. What were the first galaxies like, and how did they assemble? This allows us to study an expanding, accelerating universe when we are observing them from Earth, because we are looking at radiation that was emitted in the past. Astronomers have now detected radiation from quasars that were formed with only a few 100 million years after the Big Bang, and this gives us a great estimation for the age of the universe at about 13.8 billion years old. This gives us our first true glimpse at the earliest times in the cosmos when the first galaxies and first stars were forming, and this lets us really see what the universe began like. It's an incredibly powerful tool. This brings us to the end of our lecture on Hubble's law and distant galaxies.